So I'm going to take a particular focus during this talk. The construction industry currently accounts for around 39% of the carbon dioxide emissions annually, and 28% of that is operational, and 11% is related to construction directly. And tall buildings require a relatively larger amount of carbon in their construction than lower-rise structures. My question is, how can we justify that? What's the future of tall buildings? Is it reasonable to construct any more tall buildings, or should we consign them to construction history? I'm going to talk through the history of tall buildings up to now, particularly since their explosion at the end of the 19th century. And then I'll discuss the technology of tall building designs now, and then I'll come back to this question with some thoughts about the future. So tall buildings through history have been limited by the possibilities of the structural techniques available at the time. The pyramids in Egypt were the first man-made structures to break through the 100-meter height mark. The most famous were constructed in the 26th century BC, and the largest of them, the Giza pyramid, was 146 meters above ground level. More specific to the theme of towers, the Alexandria lighthouse was built around 250 years BC and measured around 120 meters. So it's not until the cathedral construction period of the Middle Ages that these heights were surpassed. And even after all this time, the towers were not radically greater in height from those built more than 1,600 years before. So Lincoln Cathedral, the spire built in 1311, was reputedly 160 meters until it collapsed in 1548. And there are other spires which followed around Europe around about the same period, all around about 150 meters high. So Cologne Cathedral was the tallest building in the world at 157 meters in 1880. And they're all built the same way. They're built out of load-bearing masonry, stone blocks piled on top of one another to create walls. So they're heavy, and their height is limited by three structural factors: the capacity of the stone wall to support itself, the capacity of the ground beneath it to support it, and then the stability of the entire structure against the loads acting on it, principally lateral loads. And then, of course, a further factor limiting the height of any buildings was the difficulty for anybody to go up them. So they were used for power or status or as a beacon, but not for economic reasons, because not very many people wanted to or needed to go that far up into the air. And there were two technical transformations in the 19th century which transformed that. Elisha Otis is the sort of famously known inventor of the elevator. He demonstrated, this is the sort of mythology of the invention, he demonstrated a new safety hoist at the exhibition of the Industry of All Nations in New York City in 1854. He was standing on his hoist, the single rope supporting it was cut, and the platform dropped a few centimeters and then stayed where it was. So he'd invented a safety mechanism. Plenty of people used hoists before that, but they didn't like the safety implications if they broke. And so popular history records this as the beginning of the elevators, but the reality is more prosaic. Lots of people around that period were coming up with and using and trying to invent elevators. Otis, the company, was one of them. Elisha Otis was the entrepreneur who had this one, but many others were involved in it too. The main point is that during this period, there was a frenzy of activity to fulfill an economic need for people to go safely up buildings. And the second major innovation of that period was the incorporation of structural steel into the load-bearing structure of buildings rather than only load-bearing stones. So the modern era of steel production, steel had been around for a long time before this, but the modern era was invented by Henry Bessemer, really, or he evolved a process, the Bessemer process, in 1855, which dropped the price of mild steel significantly, a factor of more than 5, and enabled it to be produced more cheaply than wrought iron. And so that really transformed the possibilities of building. And those possibilities manifested themselves first in America, and particularly in Chicago, and pretty soon afterwards, very soon afterwards, New York. So instead of the buildings using load-bearing masonry walls, as had been the case up till then, they started to be constructed as a stone skeleton. So you'll notice that this gets called a skyscraper. It's 42 meters high. The particular focus is, and in fact, this project, the home insurance building, is known as being the first skyscraper. And that's really because of the change in its construction method. But there's a debate about that, because you can see on the left those steels vertically pointing, just coming out of the top of the walls. But there was still load-bearing masonry in this skyscraper. William LeBaron Jenney, the architect, built in 1885, and then some other additions made. But if we look at others around the same period, you can see clearly the fact that there's a steel skeleton, a frame, and then the cladding is following on. So that's a transformation in building technology, that instead of building with load-bearing masonry walls, we're now building with a steel skeleton. And here's another one, the same period, the Reliance building in Chicago, 62 meters, again the steel frame, and this time plate glass and ceramic cladding. So of course, those are the technological means, but there had to be a reason for that, and there were very strong economic drivers for that in that period. Chicago and New York were growing extraordinarily fast, and land values were increasing very quickly. So in New York, land values doubled between 1840 and 1870, and at the same time, there was a big benefit, an economic benefit, in density and in staying close to the coast. So in 1816, it cost as much to transport goods 30 miles inland as it did for those goods to cross the Atlantic. So there was a good reason to stay near the coast. So as quickly as tall buildings arrived, a philosophy of their construction and their design was developed. And this is a quote that I really love from Louis Sullivan, very famous architect, one of the pioneers of the modern movement, and one of the most forward-thinking architects of his generation. And he wrote a piece called The Tall Building Artistically Considered in 1896, in which he said, whether it be the sweeping eagle in his flight, or the open apple blossom, the toiling workhorse, the blithe swan, the branching oak, the winding stream at its base, the drifting clouds, over all, the coursing sun, form ever follows function, and this is the law. That's how people wrote about architecture in those days, and we all really bear in mind that's really a phrase that has lived on ever since then. But it's just interesting to see where it originally came from. And Louis Sullivan built some fantastic skyscrapers, but form hasn't always followed function in the evolution of skyscrapers, or in fact other buildings since then. And I'm not going to go through the whole history of skyscrapers, but suffice to say that that's not always the case. There's not always a clear identity of the skyscraper with its function. And maybe the climate emergency is one way to recenter that, to measure the impact of departures from the most efficient structural response for a particular design. So, as I said, this is the skyline of Chicago in 1927, which I think has a lot of tall buildings in it. And this is the skyline of Manhattan in 1931. So there was a tipping point in these cities and a huge amount of high-rise construction through a combination of technology and economic and political will. So I'm going to move on now to describe modern technology, the modern technology of tall buildings, and I'm going to show some examples from our work. So at Foster & Partners, we work in integrated teams. I'm the head of the structural team, and we work with the architects and other engineers and specialists inside the office on projects from the beginning of the process. So we've designed structures either at competition-winning projects or through to completion around the world, and I'm going to show some of the principles of tall building construction with some of those as examples. These are the Lusail Towers in Doha. They're designed by the practice and completed for the FIFA World Cup in 2022 in Qatar. And they're 4 towers arranged in 2 pairs, 257 meters and 300 meters tall. We build, in the structural team, we build cardboard models. This is around about a meter or so high. And the idea of these cardboard models is they show the structure alone. We remove the cladding so that we just see the skeleton of the building, because we want to make structures which are logical and efficient and don't need to be hidden or have anything to cover them up. We want to see them and make them beautiful. So if I focus on this tower, a tall building is a cantilever fixed at the base and subjected to both vertical and lateral loads. The vertical loads are primarily due to the building users, and the lateral loads are, of course, due to wind and also earthquake loads, the shaking of the ground, which is mostly horizontal, a little bit vertical, but mostly horizontal loads. And those loads, those forces, are carried down by the structure to the foundations. And the most common way to resist the lateral loads in modern buildings is by using the building's core. You can see this section, axonometric section, and you can see the core in the middle there. So this is the part of the building which contains the vertical circulation, the stairs and the lifts, and also quite often the spaces that are needed to put the mechanical services into the building. But above a certain height of a building, somewhere between 150 and 250 meters, but there's no absolute rule, it depends on the building structure and the loads acting on it, the core isn't enough. The building's too tall for that. And at that point, we need to mobilize the outside of the building. We need to use the full width of the building to resist the lateral loads acting on it. And this is one method used quite often, which is to install trusses, which we call outriggers, which link the core to the outside columns in order to get the full stiffness and strength of the columns around the perimeter. So these are the Lusail towers under construction, and you can see on the right-hand side the core, which is built in reinforced concrete, coming out of the top of the towers, and then the floors and the columns following on. And this shows this same view. We're at the top of one of the towers, looking across to another of its neighbors, at the reinforced concrete core coming up the middle. And this also shows, you can see around the diagonals, the outrigger floor, which has a truss around the perimeter to equalize the loads going down the columns around the perimeter. And there are the towers viewed from the sea. So another tower now in New York, 425 Park Avenue, and this is, as you can see, in Manhattan, just off to the top of Park Avenue, quite near Central Park. And this is a competition that we won in 2012. Now, tall buildings in Manhattan are required to fit within a tapering volume, which is defined in planning rules, and it gets thinner over the building height in order to allow light to penetrate down between the buildings to the streets at ground level. And as well as doing that, the client wanted to move the vertical circulation, the core of the building, away to the side rather than being in the middle, so that he'd get a whole floor plate which was addressing directly Park Avenue, and the core would be pushed to the back. And those floor plates would be addressing the street, and they'd also, of course, get the views of Central Park just off to the north. And this is the scheme that we came up with. Once again, a cardboard model to show it, 3 views of it. And it was conceived, again, to be as minimal response as possible to the brief that we had in this case. A single line of columns, which I've picked out in red, starts at the top of the building and it bifurcates twice. It divides into 2, and it also goes back to the core behind. So you can see at those 2 levels, those diagonals. And in doing that, in bifurcating at those levels, the columns connect with the core behind. You can see in the side elevation over to the right-hand side that those diagonals are connecting back to the core. And what that does is the same thing as the outrigger was doing for Lusail Tower, which is connecting and mobilizing the full width of the building to resist lateral loads, which in New York particularly, which isn't seismic, is particularly wind. So I'm going to show you what that means in terms of the forces acting on the building and therefore the reacting forces inside the structure. On the left-hand side, you can see a side elevation, and in red, those are the compression forces coming down the columns on the front. The gray is the building core, and the red is the forces, the compression forces in the columns, and you can see them gradually increasing further down towards the bottom, and of course splitting in two every time they meet a bifurcation point. And then to the right-hand side of the cardboard model, you can see the overturning moment, and that's the bending moment which the building is having to resist when the wind blows to the side. So the wind's blowing, and the building, which is working as a cantilever, has to resist that load at the base. So you can see that line starting at 0 at the top, up at 800 feet, that's where the 800 is, and gradually increasing. And the blue line shows the total moment, which has got to a maximum point at the bottom. And the red line shows the moment which is being resisted by the core. And what you can see is about halfway up, particularly at 400 feet, those diagonals are effectively splitting the load between the columns and the core. So they're working as an outrigger. So we found this a very exciting graph because it was showing that our structure was working as we wanted it to divide the load between the core and the line of columns to make it efficient. And it's always interesting, we always find it encouraging that when we've done a competition scheme, that's what gets built. And you can see on the right-hand side the construction of the tower going up. You can see those columns bifurcating. And this is the finished structure from the front. The first view that you saw was a photo montage from the competition and from the side. So again, to reiterate, we're looking for buildings that you could take the cladding off and the structure would look exactly the same as it looks from the outside. The final tower that I want to show of ours is in Shenzhen. It's under construction at the moment, and it's 388 meters high, so one of the tallest buildings that will be built in Shenzhen at the moment. It has some associated buildings around on the same site that we also are designing. So the stability for this building is provided by a combination of the core, the reinforced concrete core, which again is off to the side, again in order to achieve big usable floor plates. You can see that on the left, combined with external columns around the perimeter of the tower. And you can see those immediately over to the right. And those are linked to the core, so there's a connection once again with trusses, which we've brought out those 5 lines of trusses and perimeter structure in order to make a combined system to resist the loads. And there's another part of the loads that need to be resisted in Shenzhen, which is true of a lot of the world, but just happens not to be true in the UK or most of the east coast of the States, which is that it's seismic. It has significant seismicity. And that horizontal shaking load imparts an enormous amount of energy into the building. And so we've used a technology called buckling restrained braces, which form part of those trusses and absorb the load. And our ability to analyze towers now has really advanced substantially. And we can now do what's called performance-based design, which means that we can analyze the behavior of the building under specific earthquake events. So this is a particular earthquake which has been modeled and then applied to the building, slightly exaggerated scale, but so we can investigate the behavior of the building under that load. And here the building is on site. You can see it on the right-hand side. Once again, the concrete core going up ahead and the perimeter columns you can see being built and the floors behind them. So I want to now move back to the original question that I asked. That's a sort of a brief synopsis of the technology that we use in our design approach to tall buildings, which is our design approach to all buildings, really. The original question, how does the technical capability that enables buildings like this to be built fit with a climate emergency and our need to reduce drastically, radically, the production of greenhouse gases? And this is a debate which is ongoing in the construction community, and understandably, there are strongly held feelings about it. So this is really an emerging science, which I'm going to give you some ideas about. I'm going to start by doing some definitions, which is useful that everybody has the same definitions to start with. So carbon dioxide equivalent is the measurement that we use to compare the global warming potential of different greenhouse gases. The table on the right shows different greenhouse gases, and you can see that carbon dioxide doesn't have the largest global warming potential, but it is the gas that's most heavily emitted, and it has a relatively long lifetime compared to other greenhouse gases. Most carbon dioxide emissions are the result of the combustion of fossil fuels, not all of them, and that's something I'll be touching on, but most of them through transport and through industrial processes which require high temperatures. So, for example, 1,500 degrees for the fabrication, the manufacture of steel or cement. Then, two other definitions. First of all, we measure the whole life carbon footprint of a building, and that's a combination of the carbon produced during its construction, which is the embodied carbon, and the carbon produced during its use, heating it, cooling it, lighting it, and that's the operational carbon. So improvements in the operational carbon, insulation, better power usage in modern buildings has reduced operational carbon a lot. And what used to be not quite so seriously considered, really 10, 15 years ago, embodied carbon, maybe 20 years ago, has now become a much more substantial percentage of the overall carbon footprint of a building. And there's a second factor that we should consider when we're thinking about buildings, and that's their users. And this is a measure, the household carbon footprint, which is the impact of the building users. So we're measuring here the greenhouse gas emissions required to produce and distribute and dispose of all household consumption over a year. And this is what economists use more often, really, than the carbon definitions that is more in the engineering and architecture world of whole life carbon. So here is an estimate of the household carbon footprints of residents, and this actually is from a study of 31,500 zip codes across the states, across America. And they haven't measured all of those individual users, of course. They're using national survey data to predict consumption. So they're taking various measures, various factors, and predicting the average household's consumption. And there's a recognizable pattern. The densest areas, New York City, Philadelphia, Baltimore, the cities, have the lowest household carbon footprints, and they're in green in the diagram. The suburbs, which surround them, have the highest household carbon footprints, and they're in red. This is something that you can see online. You can go and look across the whole of the states. But to home in, just closer in on New York, you can see exactly the same phenomenon, but just in more detail. And the primary reason for the difference between suburb and city centre is the reduction in private transport. So transportation carbon footprints are around 50% higher in large suburbs compared with large principal cities, while the total carbon footprint is around 25% higher. And this is the same information from that study expressed on graphs. So each yellow triangle is one of those 31,500 zip codes. You can see a lot of variation across them. The red series of dots is the line that is the average of those points. And you can see that, and so that's the household carbon footprint up on the right-hand side. So round about 50 tons of carbon per year per household. So the states, by the way, I use the states because they're incredibly good at gathering statistical data and publishing it. These results hold true for other countries like the UK, maybe slightly lower carbon footprints, but not substantial and considerably more than other countries. And you can see on the bottom axis population density. So that's a logarithmic scale because the changes are so enormous from a rural area at the left-hand side, very, very low density of people, to dense cities, more than 10,000 people in a square mile. The center of New York is around about 25,000 people a square mile. But of course, those are very dense cities. And you can see on both graphs, both the one which hones in on the cities and for the overall zip codes around the country, that as the density reaches a critical value, the carbon footprint for those households drops away and gradually reduces. So another study then, the same effect, but a completely separate study. This one is Professor Edward Glaser of Harvard, who's looked at the difference across the same metropolitan area. So he's looked, in fact, at many cities, and the results come out to be similar. I've selected a few of them, 4 of them. And the way to interpret this graph, or to read this graph, is that the 0 point is the point of the household carbon footprint in the center of that city. So on the bottom left, at the bottom, that 0 point is the center of New York. And then the difference between the center and the suburb is represented by that vertical bar. So the average carbon use, the household carbon footprint in the suburbs of New York is 6.5 tons higher than in the city center. And you can see that that difference is due to 3 factors: the emissions from driving, the emissions from heating, and the emissions from electricity. So heating is largely natural gas in the States, in the northern states, and electricity is quite a lot due to cooling. So you can see that the cities in the south use more electricity because they're using more cooling, air conditioning, and the cities in the north use more gas for heating, but all of them use more transport than in the city center. And a final study, just to show that other countries have the same phenomenon. This was the same question studied in Australia by Colin Beattie and Peter Newman for 4,000 living spaces across detached high-rise and low-rise housing in Sydney, Australia. And you'll see that, in fact, there's a slight variation in their operational carbon. It hasn't taken into account embodied carbon. But once you add transport on, once again, transport is the defining feature. Private transport in low-density areas is the driver of their high carbon footprint. And the final study I want to show is one that we carried out ourselves, the Sustainability Group in Foster & Partners, led by Chris Trott. And that was a study which combined operational energy as well as embodied carbon. And it did a comparison for 2 projects. One project is a tall tower in a dense city, 60-story tower in a dense city with very good public transport connections. And the other project is a 3 to 5-story building development in a low-density area, primarily used by private transport. So if we first of all look at the results for the building itself, so that's the whole life carbon without the transport consideration. And you can see some interesting things in this graph. First of all, you can see that structure, of course, is higher for a tall building. There's more embodied energy, of course there is, in the structure of a tall building than there is in a low-rise. But interestingly, it's not the largest of the embodied energies. In fact, this is projected over a 60-year lifespan of a building. That's a point that we can also discuss. But the point is that actually refitting those buildings, so the fit out of a building, that is all the finishes that you put into it, and then stripping those out and doing the same thing several times over the building life, has a huge effect on its embodied carbon. And we have, in this study, Chris Trott and his team assumed a 10-year period between each refit. When you think about that for people's houses and offices, that sort of a kind of a reasonable average. That's not particularly high. People do fit-outs more often than that. And I should say these graphs also include, for future electrification, both of the material production and of transport. So they're not just a snapshot taken today. So if we look at the side, you can see that the tall building does have a higher embodied energy and, in fact, a whole life carbon than the low-rise building, 43% higher in this study. However, the story changes significantly when we incorporate transport. So that, once again, the private transport for the low-rise development changes the story, and the overall carbon footprint in that low-rise development is higher. So tall buildings enable urban density, at which point public transport becomes economically viable and local travel distances become shorter. So walking and cycling becomes possible. And the benefits of density and working in close proximity are substantial for the economy of a country. I know that we often see this in a different way. We often think about the value of our houses or the cost of living in a city, but it's worth bearing in mind that the earnings, the productivity of a city is systematically higher than the productivity of low-rise areas. So in the United States, workers who live in big cities earn about 30% more than workers who don't, and the productivity of cities with over 1 million residents is more than 50% higher on average than the productivity of areas in smaller metropolitan areas. So my point is, of course, we often think about that in terms of the cost of living, but the productivity of cities is higher. The contribution to the economy is higher. And this gap is true both in developed countries and less developed countries. So really my point here is there's no reason for it to cost more to live in a city. There's no absolute reason for it to cost more to live in a city than a suburb. That is because of policy decisions. That's because of the supply of new development in the cities and the relatively low cost of private transport compared to public transport when you consider the subsidies made to private transport. And this slide really to show that it's worth considering that all countries are at different points of their urbanization and that every city started life as a field. So I want to draw some conclusions together from that study and really look to the future. And it's easy, in my view, to come up with lots of thoughts about the future, but I want to focus on a couple, and really my focus is going to be on things which I think are perhaps in this general discussion about the future of construction, they don't get as much notice as I think they should. Wherever possible, we should be using existing structures rather than taking down structures and building new ones. That, of course, is going to reduce our embodied energy. And where it's not practical, where we have to take a structure down, then we should recycle and reuse the materials that we remove. And that's an evolving science. But we also need to make buildings that last. So a city street can last 500 or 1,000 years, while a building might be pulled down, let's say, sometimes after 50 years, sometimes less, sometimes after 20 years. And our philosophy needs to change. We need to think of buildings as vertical streets. So the functions inside them can change, but the structure can remain. Now, I want to talk about the correlation for materials between embodied carbon and the embodied energy of their manufacture. We need to focus on low carbon materials. We want to try to use those. We should use those as much as we possibly can. And as you can see, since fossil fuels constitute the majority of energy used in material production, it's not that surprising that the embodied carbon of the manufacture of those materials is closely correlated. So at the top, you can see steel, stainless steel, very high embodied carbon, very high embodied energy, and at the bottom, concrete, which of course gets understandably a bad press, and I'm going to focus on it, but actually has per kilo a relatively low amount of embodied carbon. So I want to focus on concrete, and that's going to be, as I say, something which I think is maybe an area which isn't always focused on as much as it should be. Concrete is strong, durable, fire-resistant, and cost-effective, but it is incredibly heavily used. And you can see at the bottom of this graph, cement products and cementitious products are by far the most heavily consumed in the world, dwarfing the other materials. And that use is accelerating exponentially. So cement-related products, their use around the world is dramatically accelerating. And just a word on concrete. Concrete is made of cement and fine aggregates, sand, coarse aggregates, about this big, about 20 millimeters in diameter, water and air, and then reinforcement when it's reinforced, although a lot of concrete products aren't reinforced. And if I look at the graph on the right-hand side, when I compare the volumetric constituents of concrete to the embodied carbon constituents, you can see that 90% of the embodied carbon of concrete is due to the manufacture of cement. And there are two sources of carbon emissions from the manufacture of cement. The first is the energy in burning the fossil fuels, currently fossil fuels largely, to heat limestone up to 1500 degrees in order to create lime, to drive carbon dioxide away from calcium carbonate to create lime, calcium CaO. The second is also the carbon dioxide released in that chemical reaction itself. So there's an additional and very significant element of cement carbon which is due to the chemical reaction itself. So this huge worldwide production of cement means that it alone accounts for 8% of the world's total annual carbon dioxide emissions. And it's astonishing to consider that this universal material has not really changed substantially since it was patented. It was called ordinary Portland cement, and the word Portland came from the idea that it looked a bit like Portland stone, by Joseph Aspdin in 1827, and then refined a little bit by his son William in the 1840s. The principal codes in the UK, the Eurocodes, the American codes, are all based on this cement type, ordinary Portland cement. But there are two currently additional cementitious materials which are used to mix into that cement, which have various properties, but one of which is you can consider that you've lowered the embodied carbon of your cement by mixing them in. One of them is pulverized fly ash, and the other one, which is a waste product from coal combustion. And the second one is blast furnace slag, which is the waste product from iron and steel production. So both very high energy processes, but we can consider, or we do consider in the way we count, that the carbon due to that process is already counted in the production of the primary process that they were used for. So they're waste products. They're treated as waste products. And we should use them wherever we can. But as this graph shows, the availability of them is limited, and it's dwindling, of course, because we're making fewer and fewer. We're burning fewer and fewer, or trying to burn fewer and fewer fossil fuels. So we want to have fewer and fewer of them. And they're fully utilized. That is, it's a sort of scenario of, if you don't use these products in your cement mix, somebody else can use them in theirs. There's not an unlimited supply of them. But there is another product, or there is another approach, and that's an emerging technology, which is instead of using, or in fact, as well as using those two cementitious materials, we can also use limestone before it's been calcinated, before it's been turned to lime, that is, before it's been heated, in small amounts, as well as calcined clay. So that's clay with particular constituents. It's not any clay. There are particular elements of clay which have to be present in there. But still, there is a huge supply of that all over the world. And if we use these elements, we can reduce potentially our carbon content of concrete by up to, or even in some cases over 40%. So that's a huge reduction. And in my view, we must focus on these materials reductions as well as recycling and reuse, and I don't think this gets as much attention as it deserves. I'm going to finish by focusing on a final example of our design process and one of the tall towers that we've been working on where the structural team worked on the competition to show what I hope that you've seen in some of our other projects, this focus on lean building design, which reflects the forces acting on them and the constraints of their location. So, as I said earlier, we need to reflect resource scarcity in our designs, and as a result of that, make our designs as efficient as possible. This is the headquarters on the right-hand side, the headquarters for JP Morgan in New York City. And it's a competition that we won in 2017, and it's on Park Avenue, slightly further along from 425 Park Avenue. And this is a plan view. On the left is the plan view of Park Avenue, and on the right is the plan view of the basement underneath Park Avenue, where you can see lots and lots of railway lines directly underneath the site, and those railway lines are going into Grand Central Station, which is further south on Park Avenue. So, as you can imagine, that's an interesting particular constraint for a building. And we were told during the competition that we were given a specific response to where the columns should go down into the ground level in order to respond to that constraint. All teams were given that. But we came up with another option, we came up with another solution where we gathered our columns into what we call fans. We gather them together to points at the ground level. You can see the model on the right-hand side. There are 3 points on each of the facades, the north and the south facade, where those fans come together. And then the cutaway view on the left-hand side shows the columns inside the building, where we've gathered together the columns into 2 points. And once again, we've taken the loads down specific locations. This is the analysis of that building. You can see the model analysis on the left-hand side, and the arrow showing that we're analyzing for wind loads across the building. That's the narrowest axis of the site, 140 foot wide, a 1,400 foot tall building, so quite a slender building. And then beside that left-hand view, you can see a section and a view showing the structure. You can see on the first section the outriggers, which are mobilizing the core, where you can see all of those diagonal lines. That's the central core, which is built out of steel. And then the trusses go across and mobilize the outside columns. And then on the right-hand view, you can see the red and yellow forces. Yellow is tension and red is compression. And you can see the bracing, which is present on the east and west facades, which is contributing to the strength and stiffness of the building. So some people have said to us, are those decorative cross-bracing? No, we don't do decorative cross-bracing, we do cross-bracing. And this bracing is adding substantial amounts of stiffness and strength to the tower and reducing the steel tonnage. And once again, it's always interesting to compare the competition photo montage that we did. Here's a view from the ground level looking at those fan columns. You can see 2 things. You can see the fans on the side facades. You can also see that big inverted V, which is linking the cross-bracing and bringing it down to the ground. That's the view that we had at competition stage, and this is what's being built on site. That was a view from a few months back, and you can see exactly the same thing. The fans, the gathered steel columns on the side, and the beginning of that brace on the top. The building, in addition to this, will be 100% powered by renewable energy sourced from a New York hydroelectric plant. And there was an existing building on the site, a lower building, and 97% of the building materials, all of the building materials, finishes included, as well as the structure, from that, taking down that building, were recycled or reused or upcycled. And to my original point, and in fact one of the researchers, Professor Glaser, said when he was researching buildings, he said, the only reason you should be allowed to take down a building is if you put a taller one in its place. And to my original point, this building doubles the density of the previous building on the site. So I hope I've shown in this talk that tall buildings come through a combination of technical innovation and societal need. And a tipping point occurred around the second half of the 19th century during a period of rapid growth. And in my view, we're at a tipping point now with regards to our climate. And we need to build efficiently and reuse and recycle wherever we can and minimize the carbon in our construction. And we must consider buildings in parallel with their environment and with wider society. So increased density results in overall lower carbon emissions for the same system, for the same societal system, and it creates cities for people to live in and to thrive in. Thank you.
Thank you very much indeed, Roger. I get the privilege of having questions sent in from outside on the worldwide electric web. And we'll then take a few questions from the audience. So the first one is interesting because it's about the concept that cities are all going upwards and people are living in them as well as working in them. But there is a social question about whether that functions in the same way as a horizontal street. You have no gardens, you sometimes can't get out from the living environment. How does your perception of how cities look and are built, constructed structurally, deal with that social question?
You mean by that if people want to live in a different way, they want to have gardens and...
Well, the cities are going up, yes, and people are moving into them and living in them. Take the area around the Elephant and Castle or out towards the American Embassy. Mm-hmm. They're going up very, very, very vertically, and the living space seems small. And the construction is unbelievably challenging and beautiful, but do people want to live in it when it's done? Or are you responding to a commercial step?
So I think I'd have two responses to that. The first one is there's more than one need. There are people at different stages of their lives want to live in different ways, right from their youth through to having children, to retiring. In other words, we don't have to make one type of apartment for everybody. And the second one is, I think there's an implication in what you're asking that people have more choice than, in my view, they have. I think that people's decisions are very much dictated by affordability in places like London. Certainly mine was, ours was. And really, living in London, living in European cities has become incredibly expensive. So I would question really the point you're making that, yes, more buildings are getting built in the city centre, but the fact remains that it's incredibly expensive to live in London, and that wasn't always the case. In previous periods of London and other cities, people came to those cities because of economic hardship. They came to get a job and work there because of economic hardship. So now the fact that it's almost a luxury to be able to live in London, I think is something which is one of the things I think we should discuss as a society.
So the second question is more structural, I hope. When you look at the diagram, particularly of 270 Park Avenue,
yes,
everything comes down to a point.
Yes. And
it looks to the uninitiated like a single point of failure potential. Mm-hmm. All the load is being transferred through 3 or 4 points to the ground.
Yes.
And it just looks fundamentally worrying for the innocent.
Well, so it isn't a single point of failure. There are several points, and those points are designed for various different methods of things being removed, say it like that. So it has been taken into account the idea that the building doesn't need to can withstand different events where elements can be removed. So no, it's not a single point of failure.
Okay. Open the question to the floor. Sir, at the front here.
Oh, hello. You mentioned earlier about the buildings, the tall buildings, they have to get narrower as they get bigger. Is there a height where they have to start getting narrower? Example, the walkie-talkie.
Okay, so Good question, because actually the planning requirements vary from city to city, and I was referring particularly to New York, which has a very specific and quite prescriptive method of calculating how tall your building can be compared to how wide it can be. And it's quite a kind of complex series of rules, but basically it's all really about trying to see the sky from the street. And so in answer to your question, in New York, the height is limited by how much you set in. You can go quite high as long as you set in a long way. What you're really trying to do is allow a view of the sky from the street. The walkie-talkie is part of the London planning system, which is entirely different. There are protected views of St. Paul's Cathedral from various points, and the tall buildings have to have a discussion with relation to those views. But there are plenty of other planning. There's a whole planning process, of course, but that's one of the most particular London planning rules.
New York and Chicago, for instance, is known as the city of architecture. Can you tell me about September 11? You know, a huge concrete building like
Yes.
the World Trade Center.
Yes.
Just collapsed like a house of cards. What went wrong there?
So the Twin Towers they were actually a steel frame system. They had an external steel frame around the external perimeter. And that frame was impacted by this absolutely huge fuel load, which came into them, a really enormous amount of heat delivered into steel rather than concrete. And you could then also talk about the fact that most buildings have a reinforced concrete core, which has its own level of robustness, and the Twin Towers was a very different structure from that one. So I guess my summary would be it was quite a particular structure with a very, of course, incredibly unique load with an enormous fuel load delivered into it, which resulted in incredibly high temperatures around the tower.
Next question. And there's one right at the back, I think. In fact, two at the back while you're over there.
I've been cycling through London for the last 35 years or so, and I've seen a lot of changes in that time. And as I cycle down 9 Elms Lane towards Vauxhall Bridge, I see a horrible monstrosity before me. And all you're doing is promising more and more dehumanisation, the same ghastly 1984, although that's behind us now. What we've got in front of us, God only knows. You are promising and providing a hideous future for mankind. That's what I've got to say, and I'm glad I'm 80, not 20.
I'm sorry? You live there? Well, here. I mean, it's interesting. I'm a cyclist too, actually. But I think these opinions are entirely valid, but they, of course, have an effect on other people. So, I would say our decisions, people here, maybe some of us already live in London, we're taking decisions which affect other people who either don't or can't afford to. So I totally respect your point of view about the aesthetics of what you see as developments, but I just think we have to be aware that when we take decisions about what we like and don't like, it isn't a free decision. It still affects the rest of society.
My question follows on from what the lady over the left says.
Yes.
Apart from planning laws, is there any upper limit to the height of a building can be built?
Okay.
And also, my second question is this. When you get a tall building, a tall, slender building, how far down to the foundations do you have to go? What are the foundations made of?
Yes, very good. Yes, that is a good interpretation of that question. Point taken. So first point, how tall can buildings go? Technically, they can go much taller than they are now. So in terms of the ability for a building to go taller, the materials have the strength and the predictability, and our analysis methods have moved on substantially. Of course, the forces go up exponentially, so you're designing for larger forces, but they can go higher, and you'll be aware there are towers which have been designed. The Burj in Dubai is around 800 meters. There are towers which have been designed taller than 800 meters. and they can technically go much higher. And you're right with your second question, or at least the implications of your second question, what are the foundations? That really depends a lot on the ground conditions. So in some countries, or some cities, the ground conditions are very poor. So for example, San Francisco has pretty poor ground conditions, and foundations for towers need to go down over 200 feet to find a firm ground, which is incredible when you think about it.
When you said down 200 feet, how tall is the building?
The building might be 300 meters, so sorry to go in feet. So 130 meters down to hold up a building 300 meters high, for example. So a long way down. Whereas in New York has amazingly good ground at the south of Manhattan and just south of Central Park. And that's why when you look at a profile of New York, you'll see that you've got tall buildings in a particular area just south of Central Park. Then the skyline goes down because this incredibly good rock gets lower. And then at the south end, the rock comes back up again. So when you stand in Central Park, this rock comes out of the ground. It's amazingly resistant rock. So towers in New York, not all towers, it depends on how tall they get, can be founded on pads. They can be founded on top of the rock or just into the rock. So it really very much depends on the ground conditions is the short answer to that.
How do you do it on London clay?
So London clay is a pretty good founding material. It's nowhere near as good as a rock. It's still a clay. So you found on piles for tall buildings, and you use shallow foundations as much as you can for other buildings because shallow foundations are less intrusive and quite often less expensive.
So, chap with the beard there, been waiting a long time.
I'd be interested to get your thoughts on where I fully accept that increased density has a lot of advantages, but where you already have lower density housing with established public transit, whether it's London, France, or it's London or Paris. I'm from Chicago, so I know what that is. But have you looked at, or do you have any thoughts on, are you better off building higher density outside of where you already have some of those situations and increase the use of public transit or as part of the development? Or like you were kind of saying you did in New York where you removed the existing and built?
Okay, so understood, your question, I interpret your question as saying if you have an existing development, how do you deal with working that existing development? And of course, Paris is a very interesting example, very dense city, not particularly tall, and of course, with understandably quite a lot of nervousness when people want to try and think about building tall buildings there. So I'm going to give you one version of this, but this is a far longer discussion. In my view, there are some areas where it's quite easily decided because you're in an area which is low density, which really is a developing either neighborhood or city. And we've talked inside, with colleagues of mine or the sustainability colleagues, Chris Trott, about when you have nodes which are well served by public transportation, they can have low density around them, perhaps parks, but you've built up height around those transport nodes. I think that what you're talking about is almost that you can get onto the politics of should you be building in a particular city, and I think it is understandable that people have nervous reactions to that. Really, what I'm trying to, and I almost don't want to get too much into the politics so much as to say I want to bring to everybody's attention the reality. Yeah, the reality of the carbon footprint. So we may then have to take nuanced decisions about which parts of which cities we want to preserve for entirely valid reasons. I've lived in Paris. I can see lots of good reasons to not want to, to develop all of it. But we have to. I'm just trying to bring the information for evaluating those decisions.
I mean, what's not to like about that skyline? So, I mean, that's great. But I guess my concern is, you're creme de la creme. You can build fantastic, fantastic architects. You do the maths, structural engineers. As a leaseholder affected by fire safety, how do you ensure the quality build on these buildings? You only have to look what's happened since Grenfell. I mean, it's been disastrous for hundreds of thousands of people buying these units in high-rise, in fact, not just high-rise, low-rise buildings. So you can build fantastic buildings. But when it comes down to money, developers, value engineering, we've got these major issues. So what's your thoughts? How do you ensure quality builds?
Well, you're touching on a particular issue, which is the cladding issues that have happened after Grenfell Tower, a terrible tragedy that happened about 400 meters from where we live, and absolutely awful. And I sympathize with leaseholders who are in this incredibly difficult situation with regards to the cladding on their building. There's no other way to put it. They've got this very dangerous, very difficult situation with the cladding that I almost don't want to kind of cut across a whole story, as you're aware of trying to sort that out. There are reports the building industry is changing and incorporating changes. There was Dame Judith Harris did a report, and that's basically being incorporated into the way that we carry out and take responsibility for buildings at various stages. But I guess my main theme is I do agree with you. I think that we do need to look after the quality of the buildings, and that particular issue, that very specific issue that you're referring to is a really, really difficult one,
It seems to me that we could go on asking questions all night, and I'm terribly sorry to have to bring it to a close. Thank you so much, Roger, for giving us a fantastic lecture, and please thank him in the usual way.